Second, if you're actually taking it for mark, homework 01 is online and also on CrowdMark, and well, the details are on the assignment itself. As for Mathematica, so I will be using, I think the course will be 3/4 mathematics and 1/4 Mathematica, or maybe 2/3, 1/3, I don't know. But the programming I will do will all be in Mathematica, and Maiho mentioned that it's actually available for free on the department server Sphere. So not on Coxeter. If you log in to Sphere, you can use Mathematica, not on Coxeter. And the second way to use Mathematica is to buy it. I mean, the student edition, which is roughly $150. I don't know, maybe 160. I don't remember, but this order of magnitude. Stay in the class. Basically, I don't want people to just come, get the money, and go. So stay in the class and then claim and get a refund, and I will refund you. Okay. Okay. Also, let me remind you where we were mathematically and mathematically. So we defined the Kaufman bracket by these two relations. We found that in order for it to be an invariant, B had to be A inverse and D had to be negative A squared, negative A to the minus 2. So at the end, it's just a Laurent polynomial in one variable, A. We actually made some change of variable. We first of all renormalized by multiplying by minus A cubed to some power, the right or something like that. And then we made some change of variable. So A became Q to the negative 1/4 or something like that. The two things are insignificant. So the renormalization, of course, they are significant to be consistent with others and also to be invariant under Reidemeister 1. But from a computational perspective, computing the right is a linear time operation. It's something that you can do by hand. Even if I give you 100 crossing knot with 100 crossings, well, if I give you a knot with 100 crossing, computing the bracket will take 2 to the 100 operations at least, and well, that you can't do. But computing the right is just going over the crossings, checking for each one if it's positive or negative, counting how many are positive, how many are negative. It's silly, you can do it. So, I mean, writing the program is also equally silly, so I'll skip it. I'll just say, who cares? It's so minor, it's not the issue. Okay? Likewise, the renormalizations, the substitution A goes to Q to the negative 1/4, you could do it by hand. It's really not an important thing. So really, all I care about is computing the bracket. Now, if I had a 10 crossing knot, it will be 2 to the 10 operations, which is 1024, which is more than you can do by hand, but the computer could do it in a fraction of a second. So it's worth programming it. And in fact, later we will see that we can program it better. So the computer could even do 100 crossing knots. Okay? First, we need to remember how to present knots, and my conventions are, by the way, there are many competing conventions, and there are programs to translate between them. So the conventions are not very important. Anyway, with this convention, every crossing gets represented by X, by the letter X, subscript the labels of the 4 edges that are around it, starting from the incoming lower strand, so and going counterclockwise. So in this case, this is IJKL. For the example of the trefoil knot, oriented this way, then you'll have one crossing which is 1, 5, 2, 4. Here it is, and we've done it, so I will not do it again. Okay? And we've already started computing the Kaufman bracket, so let me just redo it. So first of all, where's the mouse? Here. So first of all, I execute the first line, which sets K, the knot, to be PD and then this in a computer readable format, or a more computable compute-like format. And when I do it, the computer asks me whether I want to evaluate the initialization cells. I remind you that there is a hidden cell here in the gray zone, and the computer asks me if I want to evaluate it, and it's just the definition of all the knots. What's the problem? Everything okay? Oh, thank you. Thank you. Okay. Though, yeah, I should have brought my own pointer, and I should try to remember it because, well, okay, never mind. Oops, sorry. Okay. So yeah, I do want all these initializations data, so I say yes. Okay, and then one extra thing is that the computer reminds us that there is one particular node that we will do computations with because it will be my ongoing example. Okay? Anyway, so now the first thing was the bracket itself, which basically was, again, IJKL goes to IJKL plus times A plus B times ILJK, and and we just represented things like that by symbols P, I, L, P, J, K. So a path from I to L, or a path to J, from J to K, or a point between edge I and edge L. See it whichever way you want. So this was the first rule. And let's evaluate it. And, well, each crossing became a sum. But now I want to expand, like the mathematical operation expand. So I expand the result of T1 and call it T2. And this is already the sum of the 8 smoothings. The problem is that, say, the last smoothing, the one corresponding to A squared, or one whose coefficient is A squared B, there should be 2 more here. So here's another one, and here's another one. But in particular, this one is, well, so you have a path from 1 to 4, and then another path from 4 to 6, and then another path from 6 to 2, and then another path from 2 to 5, and then another path from 5 to 3, and another path from 3 to 1. So this must be, did they go through everything? I'm not sure. But this looks like it's going to be one cycle, right? But I need a computer to tell, not just me, okay? Likewise, so this in fact probably is at least 2 cycles, because it has a path from 1 to 4 squared, meaning twice. So a path from 1 to 4 and a path from 4 to 1. So that's a cycle of length 2. And then a path from 3 to 6, from 6 to 2, from 2 to 5, from 5 to 3. So it's 2 cycles. Okay? But again, I need a computer to know that. Okay? So the clever trick is to simplify paths. So if you see a path from I to J, and then from J to K, it's the same as a path from I to K. So this is a rule, and I want to apply it to T2, and let's see what happens. So, well, it became shorter, but the way Mathematica works is when it applies a rule to a sub-expression, it applies it once and then moves on. So here we had 8 sub-expressions corresponding to the 8 smoothings. On each of them we ended up applying this rule once, so each got a little bit simpler, but we need to simplify it more. So we just need to apply this rule repeatedly until the expression stops changing. Fortunately, there is a command for that. And I want to show you how it works by writing a silly program to compute n factorial. Okay? So I want to compute 7 factorial. I think I already did it last time, right? I don't know, maybe today it will come out different. But here's how you compute 7 factorial. You say, let me write on the blackboard my computation so far. It's 1. Then I'll multiply it by 7, I'll get 7. Then I'll multiply it by 6, I'll get 42. Then so in other words, I keep in my mind, let's do it differently. So here is the thing I want to compute. Here is 1, which is the beginning of the computation. I multiply this to here and subtract 1 from this, so it becomes 6, 7. Then I need to repeat it. So 5 and 7 times 6 is what? 42? If it isn't 42, it doesn't matter. Okay? Anyway, so I want to take 7, 1 and apply to it the rules. Well, if the 7 was a 0, then do nothing. So take whatever the output was and output it. And if we are at kn, then k goes to k minus 1, and you replace the second thing by n times k. So let's do it to 7, 1. And this did one step. It's the 6, 7 that I wrote over there. But now let's do exactly the same thing, but with 2 slashes and a dot. That just means repeat. And it will repeat until we stop. And here's what we get. Okay? So now the term 3 in my experiment will be to take T2, so the smoothings, and simplify repeatedly using this rule. So what do we get? Good. So now certain things did not simplify. So for example, 1,4 squared is really 1,441, which means a single loop, but it first became but Mathematica interpreted it as 1,4 squared, and that doesn't fit this pattern, which is a product of 2 p's. So this didn't get simplified, but on the other hand, whenever you have a square, it's obviously a loop. So here we have a single loop, here we have 2 loops, here we have a single loop, here we have 2 loops, here we have 2 loops, sorry, a single loop. Here we have, one of the terms should have 3 loops, this one. Okay? So all I need to do is to take this T3 and replace it by, and perform the replacement. If you see a path from a thing to itself, that's a loop. Or if you see a path from I to j, but squared, that's also a loop. That's also a D. So let's compute this. and this is the Kaufman bracket. Sorry, this is the Kaufman bracket pre-substitution. Now I need to make this substitution, but all I need to do is to map B into 1 over A and D into whatever it comes out, whatever it came out, and expand the result so that it would look like a polynomial. And here you go. This is the Kaufman bracket of the trefoil knot. Now, I could have done the same for any knot. So, for example, well, I remind you that this sort of secret initialization cell defined a really long rule, which was knot 3.1 is PD this, and so on, up to, well, 248 missing terms, and then GST 48 is this long PD notation, okay? So for example, if I'll take knot 3.1 and apply to it the rule knots, I'll get its PD notation. If I'll take the knot 10.165, well, so by the way, the notation is this is the 165th knot with 10 crossing, and this is its PD notation. So now suppose I wanted to compute its Kaufman bracket. Well, all I have to do is, you know what, here I did it for 10, you know what, let's do it for 10.165, I don't know. So I'll set K to be not 1065, to which I apply the rule which converts it with its PD notation. I do T1, T2, T3, T4, and the output just as before, and that should give me the Kaufman bracket. Notice that the rule, the sort of the line contraction rule, the lines that contract, the rules that contracts two edges into one, I modified it a bit. So let me unmodify it. So let me comment out the modification and see what would go wrong. So I run it, and something went wrong. And what went wrong? Unfortunately, it's a big knot. So we're seeing an intermediate result of the computation in which something went wrong. And it in itself has 17, well, a large number of terms that the computer is not showing us. Of course, I could click here, show all. It would show everything. But then, well, you know, why don't we do it? This will be very sad. Okay, it's a big thing. What's wrong with this big thing? The thing that's wrong with it was that when I had this path simplification rule, the rule was Pij, Pjk should go to Pik. But really the paths are unoriented. And Pij and Pjk is really equivalent to Pkj. So this should have also been contracted to Pik. And I could have done it by either telling the computer that P is somehow a commutative expression, so P of ij is literally equivalent to Pji, or what I have chosen to do instead, and it really doesn't matter which one you do, is, I have to remove this, sorry. What I've chosen to do instead is to add a second simplification rule. So Pij, Pkj becomes Pik. And in fact, there should be more simplification rules, but they follow from the commutativity of multiplication. So you don't need them. So now let me let me execute it again, just as a warning. And now let me copy paste it, Control C, Control V. and uncomment out that thing. And okay, so this would have taken you, well, how long will it have taken you to do it by hand? 10 crossings, 10 to the 24 terms, sorry, 1,024 terms. You could probably do it in a few days. Okay? Anyway, so here's another so now let's turn it into an official program. Okay? So I define KB for Kaufman bracket of a PD, so something called lowercase pd, which begins with a PD, with the symbol BPD, so basically the PD notation of a knot, to be. It's a module with local variables I don't want to see again, or I don't want them to interfere with whatever definitions they might have outside. So P, T1, T2, T3, T4, B, and D. And then the first thing I do, so this is the alternative approach. Instead of adding a second simplification rule, I decree that the symbol P is orderless, meaning Pij is equal to Pji. So then in the path simplification rule, I no longer need the 2 version, 1 is enough. And then T1 is like before, T2 is like before, everything is like before, and that should output the Kaufman bracket. So I run it, sorry, I input it, then I run it on the knot 817, which is my favorite for some reason. It's always one of my first examples. And then, for fun, I create a table of, for each knot, for K running from 1 to 165, for each knot with 10 crossings, so there are 165 knots with 10 crossings. So for all of the knots with 10 crossings, I compute the Kaufman bracket of that knot, and in fact, I output not just the Kaufman bracket, but K, comma the Kaufman bracket, so an ordered pair, so that I will know which is what. And also I compute the timing of the computation, and I tell the computer to echo the results as they are being produced. So let's see what happens. Okay. Well, it's producing results. These are the Kaufman brackets. They're different, mostly different from each other, so it's a pretty strong invariant. And it takes a third of a second roughly per knot. Here's 1 to half a second. Well, it will keep running. There are 165 knots, so it should run for about a minute. At the end of the minute, we will have the full list of knots and their Kaufman brackets. We could spend some time analyzing it, but maybe not today, because what I want to do is something else. So how long did it take altogether? Okay, here's the full table. And, right, so knot number 88 had Kaufman bracket this. And it took 0.28125 seconds to compute. Anyway, right, so what I'm going to do now is to, should I explain how this works? Maybe I should. Okay? Is it okay if I waste your time with a little bit of Mathematica syntax? So, when you write a list, so 1, 2, 3, doesn't matter. Okay? Let's print it in full form. In full form, it's list 1, 2, 3. Everything in Mathematica is an expression of this form, possibly nested. So let me give you an example of a nested situation like this. So let's look at a plus b to the power 3, and again, displayed in full form. So this is really this is really the expression power, where you take the power of plus and a of a and b, and the right argument is of power is 3, because it's the cubic power. So maybe it's better to view it as a tree. So let me print this thing in tree form. So, came out too big. I can probably shrink it. Okay, so basically it's a tree with labeled nodes, and the top node is power. Well, you can see. Okay? And similarly for anything else that Mathematica does. So for example, let's compute the Kaufman, let's compute the Kaufman bracket of the trefoil node. I think K still stands for the trefoil node, and show it as a tree form. So it's a sum of -1 times what's this -1?
I think it's connected to the plus.
I think it's because there isn't enough space to show everything. So it's things are overlapping each other a bit. Yeah, maybe I was too ambitious. I was trying to show a tree which is too big. Right. So really, this -1 is just the number -1, and it's connected to the plus. Thank you. You were right. And then there is the next term is time, so a multiplication of -1 and a to the power -20, and so on. Okay? A lot of Mathematica, many clever things involve massaging such trees. So they're like operations to replace all the heads with something, replace a specific head with something, rearrange the trees in all sorts of ways. So, for example, if you look at this tree, 1, 2, 3, this expression. So as a tree, it's, just what you would expect. And if I will replace the head list, you know what? I'm being silly. Let's do 4, 5, 6, 7. If I will replace the head list with the head times, which means multiply, it will simply multiply, and we will get another formula for factorial. So if I'll do times, replace head, so double ampersand is, double at sign means replace the head. So take this and replace the head with, so the head was list, but now replace it with times, and the result is again 7 factorial. So now I'll replace the head of the big table of Jones polynomials with a plus. It will just add everything. So what will I get? Oops, sorry. I failed to execute it. Okay. The last entry is the sum of all Kaufman brackets of all nodes with in the table. The first entry is the sum of the times. It took 50 seconds to compute. And this entry is the sum of the serial numbers. So it's 1 plus 2 plus all the way up to 165, which is silly, but that's what I just computed. In fact, if you don't believe me, let's do 165 times 165 plus 1, all of this divided by 2, it should be the same. Okay. So now, well, I told you I'm interested in GST 48, so let's compute the Jones polynomial of GST 48. Okay. Roughly how long should it take? So this has 48 crossings, so it should take about 2 to the 48 operations. 2 to the 48 is 2 to the 38 more than 2 to the 10. 2 to the 10 took an average of 1/3 of a second. So 1/3 of a second times 2 to the 38 is about a few billion seconds, which is about 100 years probably. Okay, so may as well interrupt this, control dot, no, alt dot, sorry, what am I doing? Alt dot, may as well interrupt this and think of something else to do. Okay, are you with me? So in fact I'll quit Mathematica and show you the other notebooks that does it better. So it's called Faster Jones. First thing, so since I've quit and I need to restart, this is a copy-paste of the definition of KB from the previous notebook. So it's the same. Okay. Nothing new about it. And here is my first idea. So my idea is the following. So suppose I have a complicated knot. I'm not even bothering to indicate that it's a knot, okay? In other words, I'm not even bothering to define the sense of the crossings, okay? But instead of resolving all the crossings at once, why is it taking so long? Just to initialize. I don't know. I think I do know. It's probably because my internet connection is lousy and it's trying to input that figure. And my internet connection is, no, it should have run. Okay, it doesn't matter because we have time. So anyway, instead of resolving all the crossings at once, so replacing each one by either a 1 smoothing or a 0 smoothing, and that would take 2 to the number of crossings, what we'll do is we will resolve the crossings one after the other. So we will first do this. And again, there are two possibilities. It's either either it's this or it's that. And then we will resolve that one. And again, there are two possibilities. This is one of them. And then we will resolve this one, and one of the possibilities is that. And then we will resolve that one, and one of the possibilities is that. And at this point, we can already apply a cycle rule. Okay? And then so we can reduce this cycle to a d, to a factor of d, and the resulting smoothing or partial smoothing might end up being identical to some other partial smoothing. So we've seen this. So when we were trying to prove the Kaufman bracket, then one of the terms, when we were trying to prove invariance under Reidemeister 2, one of the terms in the resolution of this was a term like this, which simplified. And in fact, other terms included this and that and that sorry, other terms included this and that, and they are exactly the same. Okay? So instead of treating each of them as separate, we treat them as the same. We could treat them as the same, but with different coefficients. So all we do, now I'm a bit, oh, not responding, Mathematica is dead, what's happening? Sorry, I don't know what is going on. Oh no. Oh no. I don't know, something broke and I don't know what it is. And I think we're actually losing, everything we did so far. Because I don't know how to recover. Yeah, I'll just have to close it and restart. Sorry, terrible things happen. So let me restart it. Yeah, sorry, we lost information, but okay. So I'm rerunning this. I don't know why that happened. Okay, so here is a new program. It's called Fast Kaufman Bracket. And what it does is the following. So first of all, it has more or less the same thing, except, well, I set the P is orderless, so it's undirected. The Kaufman bracket starts at 1. It's first 1, and then it will get more and more complicated as I add more and more crossings to the mix. So basically, I start with not seeing any of the crossings, and then the invariant is 1. And then once I see the first one, it will change. Then I'll look at the second, it will change again. So I have to do the whole PD. And then while the length of my to-do list is greater than 0, I let x be the first crossing. In fact, x should have been a local variable. I forgot to make it a local variable. Let's make it a local variable. So I take the first crossing in the to-do list, and then the new to-do list is you delete from the to-do list the element x, and then I do T1 up to T4 just as before. So T1 will be the currently computed value along with x, to which you apply the rule, the smoothing rule, and then after that everything is exactly the same. And that's the end of the program. So instead of doing everything at once, I do it sequentially, and then I output KB. So I output the computed value. So again, I enter it, I run it on 817, just to see if it runs well. Then I run it for 10165. Sorry, for all the crossings for all the 10 crossing knots, but now without the command echo, and it took only 6 seconds. Okay? So we did a lot better, 10 times better. Okay? Is this good enough to compute GST 48? In fact, maybe. I'm not sure. Because it's 10 times better, but I didn't see if the betterness gets better the more crossings we have. So it's possible that this would have been enough to compute GST 48. But I can do even better. Okay? So let me do something even better now. Okay? And by the way, so you might think that what I'm going to tell you is like programming hacks. Okay? But it's, I mean, first of all, programming hacks are mathematics. I mean, you know, choosing the order by which to do things is valuable mathematics. And second, so now it will look like a hack but I will put it into a mathematical framework a little bit later. Okay? So here is my thought. So what I'm going to do is I'm going to, just like I suggested, I'm going to go over the knot. I'm going to scan the knot, do the crossings in order. But let's suppose, first I do just this crossing. Then I add this crossing. Then I add this crossing. So it's as if I have a line that scans through the knot, and below the line is what I've done, above the line is what's yet to do. Okay? And I want to choose this motion of the motion of this line optimally. I want to choose it as best as I can. Now, I don't care what's above the line. I don't care what's above the line, because what's above the line is what's yet to be computed. So I want to know how much effort was involved with what I've already done. Now, when I smooth everything below the line, I'm going to get a diagram which connects to the line, but might also have a number of closed components. The closed components are all evaluated to D. I don't need to worry about them, they're just polynomials, okay? So really what I get is, so below the line, I get a sum of pictures like this, namely crossingless diagrams, with coefficients which are polynomials, pi. Laurent polynomials in A and in A, okay? So how complex is this? This is as complex as, well, the dimension of the space of polynomials, so not so big. I mean, if we have 50 crossings, these are polynomials of degree 50 or 100, but I mean, it's not so big. And then the number of such diagrams. How many such diagrams are there? Well, if there are 4, if the computation front, this orange line, which I will call the computation front, if it intersects the node 4 times, then below it you could have either this picture or that picture. Only 2 possibilities. If it intersects the node 6 times, it will intersect the node an even number of times. So if it intersects the node 6 times, 1, 2, 3, 4, 5, 6, then there are more possibilities. It could be this, it could be, well, there are more possibilities. How many possibilities are there? Well, maybe later we will see that it's approximately 4 to the number of intersection points over 2. In fact, it's precisely equal to the Catalan number, if you've seen in combinatorics, the Catalan number either of n or of n minus 1, I'm forgetting, but the asymptotics is this. Now, okay, this grows exponentially. But so it pays to have the front be short. The shorter the front is, the fewer terms will appear in the computation at that level, and then fewer terms will need to be manipulated further and so on. So basically I want to keep the length of the front minimal. Do I have time to do it? Yeah, pretty much. So what I want to do is to put the knot in a thin position. What does thin position mean? It means, really, I want to permute, I want to present, or I want to number the crossings. You know what, let me give you an example. So here is a stupid, sorry. Here's a knot. Of course, to make it a knot, I'll have to decide which sense is each crossing. And this particular knot is trivial because you can just unwind it. But that's not the point, okay? Now, if the crossings were numbered 1, 2, 3, 4, 5, 6, 7, if they were given in this order, then the computation front would be, first of all, it would be this, then it would include that, then in the next step it will include 3, so it will include that. It would be silly, right? The computation front here is of length 1, 2, 3, 4, 5, 6, 7, 8. But I could have done a lot better. So I could have numbered the crossings 1, 2, 3, 4, 5, 6, 7, and then the computation front will move like this, and its length will never be greater than 2. So to put the knot in thin position means to number the crossings in such a way that the computation front will be as short as possible. Now, how do I choose how to number the crossings? In principle, if there are 48 crossings, there are 48 factorial ways of ordering. And if I wanted to go through all of these orderings, it would take 48 factorial units of time, which is again a lot. So in fact, I don't know how to find the optimal positioning. Okay? But so if not optimal, let's do good enough. So let's do the so-called greedy algorithm. The greedy algorithm says the following. So now let's do a complicated knot. So I'll start with a random crossing. Call it number 1. Then I'll choose a second crossing, or the second crossing, so as to increase the computation front in the least possible way. So right now the computation front is everything around these crossings, or the edges coming out of this crossing. If I'll choose this one as number 2, the computation front will be, so say in other words, I will compute number 2 now, then the computation front will be these 4 crosses, will grow by a lot. However, if I choose as number 2, so that's a bad idea. If I choose as number 2 a crossing that connects to number 1, then the computation front will grow from 4 to 6, but no more. And then the next step, I'll choose the crossing which touches the front in as many possible ways. So this crossing touches the front once, so if I add it, the front will grow to size 8. But if I'll add this one as number 3, the front will simply remain of the same size, because this is again 6. So the greedy algorithm is choose a crossing at random, then choose, and then at each step add the crossings whose intersection with the front is the longest, is the maximum. Okay? You know, I did run out of time, so I'll do it next time. But the program thin position does just that. So well, I don't have time to show. I will next time. But you know, I'll just tell you that if you enter it and you define a new program called extra fast Kaufman bracket, which is just the fast Kaufman bracket program, but into which you feed the knot in thin position. So we can do it. We can test if it gives the same answers. It does. Maybe I should have also checked if it's better on the knots with 10 crossings. So all I need to do is to change fast to extra fast. And it did do better. And now if I do it for the 48 crossing knot, again, this should take 100 years if we don't do any trickery. So let's see, it took 6 seconds. Okay, so that was worth pursuing. I think we should pursue it a little more next time. Okay. See you after the weekend, and you can turn off the video. Any questions, any comments?